We just derived equations for the forces in the rotational direction, or torque direction as you call it, and the thrust direction based on airfoil theory. Ended up with these two equations. So we simplified a little bit geometry and then added CR and CA into the equations. And now we have an equation as a function of the velocity over the blade itself, or over the turbine itself, and the length, or the chord length. We don't know the chord length, and we don't know the the velocity of the wind over the turbine blade. So now we introduce the induction factors. So we have two ways of expressing this velocity. We can either use that one, or we can use that one. And we too, with respect to this one, is that one is this one divided by sinus to this equation, to this angle, and it's the same. We can use this one, and that means this one is this one divided by cosine to that equation. That's what we introduce into the equation now. So we're taking those equations, we can put them here. So yeah, this is what I'm saying. So expressing T or dt with the expression of actual induction factor. And we can do the same thing with torque. We introduce the induction factors on the torque. You see that? So back to, if we review what we have done so far. We started with lift and drag. We changed this to torque and thrust forces. We introduced CA and CR into the equation. And then in the end we introduced the induction factors to the velocity, to the relative velocity. That's all we have done. Still, the starting point is still lift and drag. But we have some uncertainty on the way, and these are the equations. This is why we introduced the induction factor, because these are the points we're going to iterate on when it comes to the algorithm that we will use later. So I would like to write down these two equations because they are the ones we're going to use later on. So the force for one element in the thrust direction is Z times CA times Z in this case is the number of blades. CA is the simplification of the geometry of the blade. Density, length of the chord length, and then this is the velocity squared. So the expression of the velocity squared. dm equals same equation, set times CR multiplied by half times density times LC times sorry, I'll go do it a little lower. Take a look at this one. We are introducing the W squared. We're using both equations, both expressions in the velocity triangle. And the reason why we want to introduce both the actual induction factor and the rotational induction factor. So those are the two equations we have derived in order from the airfoil theory. Now we're going to go to start all over again. I don't know why I get a different value on the... So now we're going to start with momentum. What is momentum? Can anybody tell me short version of what momentum actually is physically? What is momentum in this case? We learned in fluid mechanics, you had it over and over and over again. Tell me in a few sentences, what is momentum?
It's mass times velocity.
What is happening to the velocity?
Changing.
It's changing, yes, that's the whole point. It's the change of velocity or change of direction, if you like. If you have the simplest example I can tell you, and I experienced it myself being having a summer job for the fire department here in Trondheim. The fire guys, they had fun with the summer job, persons working there. We were out using the fire hoses. And I had the fire hose for me was a pipe with water going out, and I was standing there trying to hold it. What happened here is that the velocity, you have a water velocity in the hose changing direction, and it's changing from vertical to horizontal in that direction, meaning it will give you momentum on that, or a force acting on that hose. I was standing there trying to hold that hose like this, and then actually I was holding like this, and the hose was going in a 90 degree, and the fire guys, they were actually increasing pressure in the pipe, and suddenly I was not able to hold it anymore. So I was holding to the hose, but the hose was going like that. So that summer, my nickname was Slangetammeren. Hose, I don't know the English word for it. But anyway, that's momentum in this direction as well, for the turbine as well. The velocity passing through the turbine will change direction, and that will give you a force acting on the turbine. Exactly the same way of thinking. So let's go away from the. So the change, the dm, the force in the torque direction, is simply mass flow rate multiplied by the change of velocity in the u direction or rotational direction. That's the force. What happens? Velocity goes into the turbine, goes in that direction. Wind velocity is going to rotate at the outlet of the turbine. And that is changing. So the rotational velocity will theoretically go from 0 to something behind downstream the turbine. And that will give you a force acting on the turbine itself. So in this case we call it dm, and that's the mass flow rate, kilograms per second. So we can write that as density times an area. And again, now the area is for the donut we have been talking about for each element. And then the velocity 2, v2, is the velocity over the blade itself. V2 is, can write like that. dm is simply density times dA times velocity. Velocity multiplied by an area times the density. It should be a mass. 30 kilograms per. Yeah, that's correct. And then the change of velocity, the delta U, from 1 to 3, meaning from far upstream to far downstream of the turbine. I'm sorry, I was a little bit confused about whether this was correct or not. And then we introduce the induction factor, and we get an equation dm as a function of the velocity far upstream and the induction factor. You see, so that's the change of momentum. And we can do that the same thing in the thrust direction. Exactly the same thing. It's a change of velocity in that direction. So it's dm and the velocity in the actual direction. The change of velocity in the actual direction. That's delta V from 1 to 3. 1 being far upstream, 3 being far downstream. And now and then we introduce the induction factor, and then we have another equation for the momentum over the blade element. So what we end up with these four equations. We have two equations from the airfoil theory, and we have two equations from momentum. And they are both acting on the blade element. So now we can say, okay, the dt from the momentum equation should be the same as the dt from the blade element equation. And the same with the dm. And now we have equations we can play with. These are the equations we're going to use from now on. And yes, they seem complicated, but still they come from a relatively simple physics. And that is what you have to bear in mind all the time. So if you lose track, go back to the physics and then start over again and go through the equations. If you lose the physics when you're doing the programming, you have no control. Questions about these four equations? This is the key. This is the key element for the whole algorithm that comes later on. Okay, let's combine them. So we set the momentum equation and the blade element equation for dt to be equal to each other. And the same thing for dm. So let's go for the thrust direction first. We have the two equations, and then we can start to eliminate uncertainties, and then we can find an expression for the actual induction factor. This is the point, because now we're going to the blade element momentum method is actually going to find the value for the induction factors for you. And once you have the induction factors, you have the triangle. And when you have the triangle, you can go on and find the CL and CM, the lift and drag coefficients, and so on. So it's simply the momentum equation and the blade element equation put together, extracting the induction factor, the actual induction factor. Again, we introduce solidity. We call it just a factor, but again, we define a factor in order to reduce the equation size. And we can do the same thing in the torque direction. And now we can extract the tangential induction factor. So that's the key. This is the key. We have equations for the forces and we have equations for the induction factors. And now we can start to iterate actually. Now it's possible for us, we know we have enough equations for an iteration in order to have an optimum, to design an optimum blade. Please go back and rewind and do this one more time and make sure you understand these equations. Until now, the only thing we have done is going from blade elements, airfoil data, and momentum equation, and then found an expression for torque and thrust, and then also an expression for the induction factors. That's all we have done. Before we go into the actual algorithm, I will just tell you a few things about tip loss and what to do. You do not, when you do exercise 3, I don't want you to introduce tip loss. But maybe as a team, as with an optimum turbine later on, you want to introduce it into your algorithm. But please don't so far. But the tip loss is, as I expressed it before, is simply due to the pressure difference between the upper and lower part of the blade, which introduces a swirl. And in the compendium you will find equations for that tip loss factors, and it is possible to introduce that into the blade element momentum method. It's quite common to use it as well. But I simply advise you not to use it in the first round when you are when you're making your own model. So I'll come back to that later. Let's start with the algorithm itself, the way you're going to design or program your system. You need to have a way of thinking first. First we have the equations, the momentum equations. And we have the expressions for the induction factors. So let's start with the algorithm. We will find induction factors for each element, meaning each annulus or part of the blade, so that you're back to the way of thinking you were when you actually had exercise 1. So for each element, you can decide how many elements you want. So if you use MATLAB, you can choose 1,000 or 1,000,000 if you like. The input factors are the description of the blade. And you already have a description of the blade from the first exercise. You have the chord length, you have the twist angles at different foils, and we have the airfoil for each element with CL and CD, and you have the properties of the airflow, and you have the upstream wind speed. And you have chosen a rotational velocity. By choosing TSR, you have chosen a rotational velocity. There is one thing for each element, or I guess if you choose to use the same blade for each element, and I think you will, and I hope you will, at least for the first iteration you should, then there will be an optimum ratio between CL and CD. And that is given to you, that is not given to you, you have been given a table of CL and CD values at different angles of attack. And then you find the optimum CL over CD, and that's the number you want to achieve in order to have an optimum turbine. We would like to have an even load distribution. And since the velocity, rotation velocity changes over radius, the length of the chord length will change. I really would like to encourage you to choose one blade, one airfoil at the first run, and you choose one optimum CL over CD, so that this is what you're aiming for in your iteration, to have the optimum CL over CD. Okay, let's start with the algorithm. You start with the blade design, and that blade design is coming from exercise 1. So you have 10 elements, you have twist angles, and you have chord lengths. And then you have the conditions, like you have the wind velocity, density, and the rotation velocity. You have to choose that. And then you do the iteration within the program you're going to make, and out comes torque and thrust forces for each element. So what you do, you calculate what you actually have, and then it comes out as a number. And then you calculate the thrust and torque, and you calculate the power. And when you have the power, you're able to calculate the efficiency of the turbine. And now you haven't changed anything. What you have found is simply the induction factors and the torque and thrust forces acting on the blade. And you might have an efficiency which is very low. And now comes the trick. After that time, you need to change something. And that something is either the twist angle or the chord length of each element. We are not going to introduce Gillowatt correction yet, but we can do that later on. But let's start with the complete iteration. A full set of equations. You start with the blade design, twist angles, chord lengths, radiuses, whatever you have from the first exercise. Density, velocities. And then you set an initial value you actually guess the induction factors. You can guess it to be 0, or you can guess it to be the optimum values. Doesn't matter. And then you calculate the angle of the flow angle, because now since you have chosen the A and the induction factors, you can actually calculate the velocities in the velocity triangle. So we have chosen those two. So that means you can calculate all components in the triangle and then find that equation, that angle. And based on that, you're able to find the angle of attack for each element. When you have the angle of attack, you can look up and find lift and drag coefficients. And then you have those, you can calculate CA and CR. And then you have that. And now you're able to calculate the induction factors. We have two different factors for different areas. If the actual induction factor is less than 0.2, then you go for this equation. If it is higher than 0.2, then you go for that equation. So we calculate A and A prime. And then you test, is the calculated induction factor close to the ones you actually started with? And most likely, not first iteration will be far off. That they should be at least the differences between them should be less. In this case, less than 10 to the minus 6th. And if it's not the correct value, then you change the guess of the induction factors, and you iterate until you have convergence of the induction factors. That's when you know how the flow, that's when you know how this is actually what it looks like on your turbine, on each element. If it's okay, then you can calculate the blade element parameter, which is an introduced factor. And then you calculate the chord length. And you calculate the thrust and torque forces on the blade, each element, and then you calculate the torque, power, and power factor. And now we have the efficiency. And you have to...
In the step 3, when you calculate the angle of attack, how do you know the twist angle of theta? Do you take the first one, the fast one?
You have the velocity of the wind far upstream.
Yeah.
You have guessed that one in step 1. You have the rotation velocity because you know the radius of your element, you know the rotation velocity, and you have guessed that one. And this is
Yeah, my question is for theta. It's phi minus theta, or alpha.
alpha is 5 minus theta, yes.
And then the value for the twist angle, not the, like for, do we take the first one we had for exercise 1?
You mean the alpha, the twist? Yeah, you have twist angles already, yes. You have
We don't change it.
no, you have to start with something and then you change it later on.
But then the twist angle we calculate in exercise 1 will be the same.
Unless you change it later on.
Okay.
That's a good point. You will have to change it in order to optimize your turbine. So that comes now, because now at number 12 there, I want to find out if my efficiency is good enough. And most likely, the twist angle is way off. It's not going to be good. So we have to go back and then twist it or change the length of the blade. So that is the point. So on the point from 12 and back again, you need to change the geometry of the turbine. And yes, you're right. On that line, there should be information about how to change the blade. It should be either the chord length or the twist angle you should change when you go back from 12 and then start over again. So you need to do some changes there. That's the blade element momentum method. That's how it works. And out from this, you're able to calculate the forces, the chord lengths, the power output, and so on and so on. So that's the algorithm you're going to write in your program. Any questions? How many of you can say that you're familiar with MATLAB, knows it well? Wow, yeah, that's good. That's very good. All right, if not, then I'll see you in 1 week.